All right, so it's been a little while since I've shared an update, and to be honest, it's been a little slower on my end than I was hoping it would be. I've just been too busy with work and whatnot. But I have been busy working on Castle as well. I did go up to the Consumer Electronics Show, or CES, in Las Vegas in January to actually to do a lot of things, to speak with companies about getting my circuit board, my printed circuit board done, getting the casing manufactured, as well as I spoke to a lot of component manufacturers who would actually have components that would go into various places on the circuit board itself. So, couple of kind of cool things you can see here, and this has been in place for a while, right? That's the Raspberry Pi compute module, or that's the compute module 2, or CM3 actually. And what I've got now is I actually have a CM3. So that's a compute module 3. You can see that it slips into that DIMM slot on that board. That board is an eval and a test board for the CM3. It's convenient because it gives me access to SD card, a breakout of all the GPIO and others, display. The bad thing is it doesn't have any network connectivity on it, which that's fine. What I will be using this for is really to do the wiring that I need to do for connectivity ultimately to some of the other components. So to the data acquisition components, to the power coming in, to the network and externals. Right, I'll use this to enable those functions and test out that circuitry. The other update, I suppose, is what we have over here. So this is the breadboard that you've seen before. This is one of the Raspberry Pis that I have. That's Raspberry Pi 3B Plus. Has everything I need on it, and I'll use that for a variety of things. Here I'm just using it simply to draw power off of. I'm using it simply as a source for 3.3 volts of power into the breadboard over here. Now, I suppose the coolest update is these two pieces here. So this is an eval test board. This allows me to actually connect to a specific board, such as this one here, which is an eval board for a specific circuit. So if we look real close, you can see this little black, let me see if I can't see my finger, that little black thing right there. That's the circuit that is being tested on this board, right? So that circuit is what's called an analog to digital converter, or an ADC. That particular one is the Analog Devices LTC 2499. That is a 24-bit 16-channel ADC. What that means is I can measure the voltage on up to 16 individual channels on there to 24 bits of precision. If we go back and we look at the original circuit board, you can see in the data acquisition area where my ADCs are. My initial thinking was that I might use something like the Microchip MCP3424, which is why you see so many components list or shown here. The MCP3424 is only a 4-channel ADC. So my thinking was, if I was going to be doing 32 channels, 32 circuits, I was going to need to have 8 ADCs to measure those. And because of the way the MCP3424 works, to do what I wanted to do, I actually had to have 16. So you're basically measuring 2 channels with each chip. What I have here, the LTC 2499, because it is a 16 circuit chip, I'm actually able to do 16 channels per chip rather than 4 channels per chip. So significantly greater number of circuits can be handled, 4 times the number of circuits on a straight measurement. and because of the way measurement was going to have to be done, I'm actually getting 8 times the measurement on than on the LTC 2499 than I would have gotten on the microchip MCP 3424. So this is just a schematic of the 2499, and this is actually what the 3424 looks like. So a slight change in terms of what I was expecting would be built into or onto the motherboard or the circuit board. Again, the ADC, or the data acquisition circuitry, being changed from here we've got 16 chips to only going to 2 chips. So now let's actually look at what this is doing. So the way that I have this set up right now is I'm drawing 3.3 volts of power onto the breadboard, and I'm using that to supply power to, you can see here I've got black, that's actually my ground. I've got green on one channel, and I've got red on another channel. And I'll show you an image, maybe a little bit easier to see on this. The individual channels that are on the little turrets where things will be connected to. So now what I've got shown here is I'm actually showing the software that runs on via this module here, which gives me the ability to read data off of this and test with. Now where I will ultimately go with this, or the next step, would be to actually provide a connection between this board and the Raspberry, which allows me to read the data off of here and actually then take some action with it. That would be the next step from here. But if I turn this on, so we are on 0, 1, 2, and 9. We're on channels 2 and 9. So if I enable data collection, what you're going to see is that we are now taking measurements of the voltage that's coming across. In this case, it's channel 2. And you can see there where it's showing it's 1.653 and then some variant. And that, you can see all of the positions there following the decimal point. That's because of the 24-bit precision that this chip is capable of. I may not use it in 24-bit. I can change it from 24 to I think we can go 24, 16, 8, maybe 4-bit, although probably 8 would be about as low as I would go. So that's on channel 2 there. Now let's pause it and let's move to channel 9. Okay, and now I'm measuring on channel 9. Now, coincidentally, they happen to be measuring the same value because they're both measuring. Their power draw is being provided by the same source, so it's the same value. But the point there is, if I had wired this up and had 16 individual cables running over here, I could be measuring actively on 16 different circuits simultaneously and acting on them individually, right? So you can see there again, we're measuring the 1.653. What will happen when this is put into practice is, if I disconnect circuit 9, right, which was basically, if you remember the previous videos, we had an open circuit and a closed circuit. When a circuit is closed, generally speaking, that's when a door or window is going to be closed, and when a circuit is open, that's when a door or window is going to be have been opened. So we'll do an open circuit here, and what you're going to see is that we stop getting data, right? There's no voltage there to be measured. Which is to be expected, right, at this point. But what will happen in practice is I will actually put a pull-up resistor in place that allows me to draw a very small amount of voltage into this circuit, so that when this is disconnected, what happens is I don't go to an unreadable state, but I will drop down only to reading what is coming across via the pull-up resistor, which ideally is going to be something like a 0.01 volts or something in that range. And then obviously the difference in the voltage reading tells me, do I have an open door or a closed door? And in some situations where you may have what they call wire monitoring, which allows you to monitor for whether a wire has been severed, right? You potentially have the ability to also do wire supervision, which is one of the things you'll find on some of the more advanced traditional wired alarm control panels that are out there today. So anyway, there's an update for you. Again, what I plan to do from here is connect this device to the Raspberry Pi. That connection will be done over what's called an I2C bus. That's basically a two-wire bus, which would allow me to read over those two wires the value for all 16 of the channels that are on here, and actually